Hello? Check. One, two.
Yeah, perfect. Good morning, everybody, and welcome to the plenary session this morning. My name is Christoph Graf. I'm Vice President for the Technical Program of TIRENA, and I'll be your session chair this morning. In this session, we will talk about the outlook for networking in the face of rising demands, advanced applications, collaboration, new technologies, and their interaction. Then we will talk about the use of state-of-the-art networking in support of e-science and the great benefit to researchers in many disciplines. As our first speaker, I'm welcoming Pradeep Sindhu. He founded Juniper Networks in 1996 and is currently Vice Chairman of the Board and CTO, and thus responsible for the company's technical roadmap and the design and development of future products. Before founding Juniper, Pradeep was principal scientist and distinguished engineer at Xerox's Palo Alto Research Center. The new network is the title of his talk. Pradeep, the floor is yours.
Thank you. Well, good morning, everybody. I want to talk about a concept that we call the new network. I want to talk about the principles on which the new network is built, its architecture, and of course, its applicability or its application to research and education. I want to make a few general remarks first, then I'll talk about the high-level architecture. I'm also going to talk about computing and storage, not just networking. And then for the network, I'll break the discussion up into really several parts. First of all, the core network, which is very, very important to science and education. The campus network, which is a key part of the reason for why there are bottlenecks today. Two major trends of cloud and mobility which affect everybody, including science, and then virtualization and programmability. So those are the topics. So let's start with some general remarks. Well, our industry, the networking industry, but even more broadly, the IT industry is facing a fundamental challenge today. And the challenge really is that the revenue, or in the case of people who are users or in the enterprise, the benefits, the costs of equipment and infrastructure is increasing faster than the benefits are increasing. And the bandwidth requirements and the number of services is exploding at exponential rates. Now, for any business like a carrier that is trying to run a real business, if costs become higher than revenues, you obviously don't have a business. This is not a healthy situation. So it's very important for people who participate in this ecosystem, like my company, Juniper, to actually try to find a way out of this conundrum. And the way out of this conundrum is really what we call the new network. So to characterize the new network as different from the old network was consisted of a bunch of specialized networks, one for each application. This was relatively inflexible. You had siloed infrastructure and operations. In other words, both the equipment was specialized and the people who ran these networks needed to be specialized. You had typically one killer application per network, maybe voice for one, broadcast television for another, and so on. And in fact, the use of the network, the rate at which people were using networks, was relatively slowly growing. If you now come to the new network, it's actually radically different. You have a network which is horizontally based. In other words, you have layers of the network. There's one homogeneous network and networking technology. The network is programmable. The infrastructure is shared across, both infrastructure and operations are shared across all applications and users. instead of having a few killer apps, you have a long tail of apps. If you look, for example, on the iPhone or an Android ecosystem, you see that there's not just one or two applications. There are hundreds of thousands of applications, some of which are used very infrequently, some which are used very frequently. But the tail of the distribution is very long. And of course, you have a situation where the usage of the network and the infrastructure is growing exponentially with time, not slowly. Now, this new network happens at the core of a much, much broader trend in industry. And this broader trend is really that the global information infrastructure around the world is being re-architected as a result of some fundamental trends, which are escalating cost, the preference of users to consume information anytime, anywhere, and a network and networking technology which is becoming more and more powerful. So those are the three factors. If we look at this shift will transform all industries that are associated with producing, consuming, storing, processing, and transporting information. So it will not, like the internet, it will not leave any aspect of computing, storage, networking untouched. And of course, it's going to provide huge benefits to end users. We also believe that this new network paradigm will be at the center of this transformation. And in fact, all systems that are unconnected will become useless. And we've already seen the beginning of this trend with the internet, but this trend is going to accelerate. Now, the central theme of this broader trend is centralize what you can, distribute what you must. This is an organizing principle for what we call this new information infrastructure, which is, some people call it cloud computing, but in fact, it's broader than cloud computing because it's cloud computing on the one hand and mobility on the other hand. Those are the two super trends. Now, the new information infrastructure has really three broad parts. If you zoom up to the highest possible level, what you see is that on one side you have, and this is obviously not a picture of today, but this is what it will look like in the future. You have large-scale data centers on one side. You have a global high-performance network in the middle. And then on the left-hand side, you have the endpoints, either locations or devices through which people and other endpoints will access this infrastructure. May I ask for some water, please? So this infrastructure has really three parts, and we'll talk a little bit about each of these three parts as we go forward. Now, thank you, Jean-Marc. The new network, and in fact, this new information infrastructure itself, the architecture is based on four fundamental principles. As a company, we are actually very careful that when we talk about architecture, we make sure that the architecture is based on something which is solid. And something solid means it's principles that you can depend on independently of a current fashion or fad. So what are the four principles? Well, the first one is that the infrastructure must deliver information to end users anytime, anywhere, across any type of device on a worldwide basis. This is absolutely fundamental, and it is the basis for why the internet has been so successful. A very important assumption is that the end users are not just human beings. They could be any information processing system. So many times people make the mistake that, hey, it's just human end users. No, in many cases, the end users, if you want, could be sensors, could be actuators, could be machines which are working automatically. They're as legitimate clients as human beings are. The second principle is that we need to build the infrastructure using a small number of programmable building blocks that can be virtualized on one side and then shared on the other. So the most important thing is that the building blocks must be independent of the applications and users. Why is this necessary? Well, in the world of killer applications, you could specialize the machines. But if you have 100 or 200,000 applications and counting, it's impossible to specialize the infrastructure to a specific application. It just doesn't work. The second one is that we have to minimize the CapEx by amortizing the equipment over as many users and as many applications as possible. This is the only way that you can actually conquer the cost problem that I mentioned in the very first slide. The third principle is, in fact, a fundamental principle of all advanced technology, which is that we must try to automate everything that can be automated. And the reason for this is that this minimizes OpEx by converting manual labor into automated tasks. We'll talk more about automation in a bit. And then the last principle is that we need to provide an open software ecosystem to maximize the rate at which innovation can happen. So those are the four fundamental principles on which the new network is based. Now, the very first one, connect everything, empower everyone. This principle really says that networking is powerful only when networks are fully connect all of their users. You've seen this with your own work as universities collaborate with each other, as researchers around the world collaborate with each other. The benefits are maximized only when you have a fully connected network. So we've had at Juniper a principle, the vision of the company really is connect everything, empower everyone. And the basis of this is that all information systems on the planet must be connected into a single global high-performance network, because this is what maximizes their effectiveness. And out of all the companies that are in this industry, we've actually been pretty unique in making some assumptions that the network is based on the Internet Protocol and MPLS, not a whole bunch of other technologies. We've been unique in assuming that end users are not just people. They can be anything that can produce, consume, process, or store information. We've also been unique in assuming that the applications that are running on top should be any communication application permissible by the laws of physics, not ones that particular companies decide are popular. What applications will eventually run? I mean, today, when you look at computers, you don't ask the question of, oh, is this computer built for only this application? No, they're general purpose. Well, in that same way, networks are going to become fully general purpose. And of course, we assume that the network must be designed to handle global scale. And that global scale today is 10 billion devices, and this number of devices is actually growing at a very fast clip, much faster than the rate at which human beings, the population of human beings is growing. Okay? So the second principle, programmable building blocks, the way this works is that if you look at any technology, take, for example, microprocessors or computing, or you take storage, what happens with this technology is that early in the development of the technology, the performance is very limited, and so you are forced to actually build devices that are very specialized to applications. It's necessary. But what happens over time is, as the technology improves, you come to a very critical moment when you can build a single technology which is powerful and general enough to actually support a large number of applications. And when you get to this critical point, you enter this very positive feedback loop where you have a general purpose device, applications on top of it, increased use, and that increased use spurs further development of this technology. And now you reach this, what we call the platform effect, with exponential and exponentially growing performance. At the same time, if these devices are general, you also get the economies of scale, because as these devices get used more and more, the cost of them starts to drop. We've certainly seen this with a microprocessor and with computing. We've seen this with storage. And now we're beginning to see this with networking. The third principle, which is automate everything, as I mentioned, this is a principle of really high technology. It was true in the days of early days when the plow was invented for agriculture, as it was for the steam engine, as it is for the computer. And basically what it says is that, look, anytime you can take tasks that need to be that are being done manually and convert them into automated tasks, the cost of automated tasks will fall exponentially as the technology improves with time, but the cost of manual labor keeps going up with inflation, typically. So you don't have to be an economist to actually understand that, hey, I want to be on the blue curve, not on the red curve. So this is a very, very important principle. And this organizing principle, which says centralize what you can, distribute what you must, is a way of organizing the information infrastructure so that I can actually easily automate it. That's the only reason that you try to centralize. The last principle, which is an open software ecosystem, basically says the following thing. I'll give you 3 examples from the past. The first one is System 360, OS 360, which comes from the 1965, 1967. The next one was the IBM PC and Microsoft Windows. And a more recent example is the iPhone and the App Store or the Android ecosystem. In all these cases, you had the same phenomenon of, the iPhone took telephones from being single-use devices to fully general computers. And then Apple opened up this ecosystem so that lots and lots of people could write programs. And as a result of that, you saw very, very fast increase of these devices. And as a result of that, the iPhone has been improved progressively every year or every year and a half to be more powerful. And of course, now you're in this positive feedback loop. So the high-level architecture of this information ecosystem consists of the following layers. At the very top, you've got what we call mega data centers. And mega data centers are locations that contain large-scale computing and storage facilities. It is the place where applications are delivered from and the place where applications actually run. They're also the control points for the rest of the infrastructure. And finally, and very importantly, it is the single place where the master copy of long-term persistent state is kept. And the reason for that is actually very simple. If you want to simplify and automate the handling of the rest of the infrastructure, you have to consolidate and centralize this long-term state. If you don't do that, you're never going to be able to automate the rest of the infrastructure. Excuse me. The next layer down in the architecture is what we call the supercore. And the supercore's purpose, if the purpose of the mega data centers was to do computing and storage at large scale, the supercore's purpose is to actually connect these data centers to each other and to the users down below. And these supercores don't do anything other than switch traffic from one place to the other in as flexible a way as possible. The next layer down from that is what we call the universal edge. And the universal edge contains equipment where communication services get defined. And you'll see that in any scalable network, you actually have a hierarchical organization out of necessity, because otherwise you can't scale it. And this hierarchical organization means that at the edge, you have relatively more complicated devices, and in the core, you have relatively simple devices. And this is a way that both technology favors and the organization of the infrastructure favors. And finally, you have what we call the access network, which is primarily a passive optical network, either directly fibers connecting premises or radio cell towers that connect users that are mobile. And at the end, of course, you have the end users. Now, large-scale computing is something which is very, very important to science and technology, and very important to the agenda of research and education. It turns out that there are two fundamental principles for building large-scale computers. The first one is that if you try to take a bunch of computers and build a larger computer, the worst possible thing you can do is to spread these out over distance. Why? Because the speed of light, as these computers interact with each other, imposes that these interactions will be slow. And so performance dictates that you should try to group these machines in one geographical area. Now, obviously, there are limitations to this. You don't want to put all your computers in one location because of reliability problems and because they might become too far away from end users. But there's a happy medium which is data centers which are much, much larger than the data centers that we have today. For example, if I look in R&E, most universities and research institutes have their own data centers and their own machines. And in fact, in many cases, when I was at Carnegie Mellon, and I know still this is the case in the United States, that almost every department has its own computing facilities. This is a very, very inefficient way to do things. If you try to distribute things, one other thing that happens, which is that you cannot pool the resources together to get efficiency. And the pooling, in fact, goes as 1 over square root of n. So if you have n silos of machines, the efficiency drops by a factor of square root of n. This is something that Peter Denning actually proved in his PhD thesis, I think in 1964, 1965, long time ago. Now, both of these principles argue for large-scale, virtualized and shared data centers. Now, it turns out that the key performance bottleneck, or the key bottleneck in building large-scale data centers is actually the internal data center network. And technology limitations with the speed of microprocessors actually exacerbate the problem. It turns out that I can't build individual cores to be very fast anymore, and the rate at which their speed is increasing is quite slow. And so what I have to do is to build a large-scale computer, I have to combine tens of thousands of these smaller computers together. The moment I have this problem, I actually have a very difficult networking problem to connect these things together. So the stage is set for a fundamental disruption in computing and storage, and we believe that networking technology, a specialized networking technology which is like the backplane of this computer, will be at the heart of this revolution of building large-scale data centers. Let's take a look inside a mega data center. We see that there are several components. There are 6 components, in fact. You have servers, horizontally scalable. You have some storage. You have appliances that you might be using for security, for running firewalls and to protect the data center from malicious users. You have, of course, routers to connect yourself to the outside world. You have a data center manager, which is a piece of software that allocates resources inside the data center. And then in the middle, you have what we call this fabric, which connects these resources any to any. And this fabric has some very important properties, which I've listed there. Any-to-any connectivity, fair and non-blocking, very, very low latency and jitter, because these are aspects which improve performance. In fact, they're necessary for performance. No packet drops when congestion happens, linear cost and power scaling, support of virtual networks and services, and a modular distributed implementation so that you can scale and pay as you grow as opposed to paying upfront. And then finally, you want a network which looks and feels like a single logical device so that the network administrator is not overwhelmed with the complexity of the number of devices that they have. Okay? Let's talk about the core network. A fast and cost-effective core network is absolutely critical to R&E. There are many, many applications where you're generating tens of gigabits of data, hundreds of gigabits per second of data, and this data needs to be shared and used by researchers around the world. Now, historically, not just in the R&E community, but around the world, there have been multiple dimensions to the debate for how you should build a core network. And these debates have gone along the following dimensions. Should I use packet switching or should I use circuit switching? That's one dimension. Another debate is, should I use electronics or should I use optics? And third debate is, what should the architecture look like? Should it be integrated, where optics and electronics are integrated in one machine? Or should I have overlay networks? Or should I partition the network into a core which is optical and edge which is electronic? Now, unfortunately, these debates have been infused with more religion than science over many, many years. And these religious debates have happened primarily because either the funding sources are tied to doing things in the optical domain, or because vendors of equipment have a particular agenda to promote. But I would say that today, by and large, from a technology perspective, these debates are relatively settled. So in what direction are they settled? They're settled in the direction that clearly packet switching wins hands down over circuit switching, and it wins because of basic laws of economics. And in this day and age where the funding is, we don't all have 10 times the amount of money that we can use. We actually have less money than we need. So we have to make more effective use of the infrastructure that we have. And packet switching is clearly superior to circuit switching. Debates that people had about packet switching being slow because it's implemented in electronics, this is not true. It hasn't been true for a decade, and it's even less true now, and in the future it'll be even less true. Then the debate about what should we use optics for, what should we use electronics for. Well, the laws of physics tell us very clearly how to divide these things. Optics is very good for point-to-point transmission, and electronics is very good for anything where you want to do switching at fine grain, or you want to do some kind of control. Electronics is the only way to go. Unless we have some revolution in the laws of physics, this is the way that things will remain for a long time. And then finally, on architecture, we believe that an integrated architecture where you have a new kind of device which integrates optics into an electronic device, which we call a supercore router or a transport router, is the way to go. Because this gives you the best economics. If you have overlay networks, you're building networks multiple times. You have different administrations at different layers, and it's very expensive to operate. So these trends tell us that we have a new kind of network element, which we call the transport router. This new network element is extremely high speed, does very low cost packet switching. It has direct implementation internally of 10, 40, and 100 gigabit Ethernet optics. And these optics can go over very long distances, distances of 2,500 kilometers. And these devices are also very tightly integrated with purely optical devices such as DWDM multiplexers and ROADMs and amplifiers. So if you look at this converged supercore, what you see is you have these devices, and right beside these devices are drawn as circles. Right beside them you have DWDM multiplexers, and I haven't shown the amplifiers, and the red lines are, of course, the point-to-point circuits. And that is what the supercore is going to end up looking like. And outside the supercore, you have, of course, these edge devices. Let's talk for a second about the situation inside a research and education campus. Oftentimes, while we might have a very nice core network, when traffic gets into the campus, all of the nice properties that we had of low latency, low jitter, and very little congestion starts to get destroyed as I run through a not so well designed campus network. So our view is that the design and the architecture of the campus network is equally important, because otherwise you're going to throw away all the money that you spent, or at least not throw away. You're not going to get the benefit out of that expenditure of building the core network that you could if you built this campus correctly. So let's take a look at how the campus might be designed. Let's suppose that this campus has two buildings. Let me call them Building A and Building B. And there's also a local data center. And the reality is that for quite some time, we will continue to have local data centers. What I would like is at the edge of each building, you have what we call these universal edge routers. And what these universal edge routers do is that is the point at which all of the communication services that you want to support are actually defined. This is where the policy for whether you're a student or a researcher or staff, how much bandwidth you get, what kind of protections you get, what kind of latency and jitter qualities you get. This is where these policies are defined. And these policies are not defined individually on each machine. They're defined per user. So independently of whether the user is sitting in Building A, Building B, or is a mobile person, those policies follow the user around. If you look at the network below these universal edge devices, that network needs to be a much, much simpler and faster network compared to what we have today. So today we have really a hodgepodge of complicated Ethernet switches below. It turns out that the network that is sitting below these universal edge routers primarily needs to switch traffic north and south. There's no need for peer-to-peer communication inside these buildings. And if there is peer-to-peer communication, it can always go through those edge routers on top. They're way powerful enough to allow you to do that. Even if every individual is having a video conference with every other one, you can still support that. And of course, you want to support very high bandwidth connectivity to the local data center. So the architecture really looks like you have a campus with a bunch of buildings. Each building has its own pair of universal edge routers. And these buildings are connected with very high-speed optical fiber. And of course, these edge routers are also connected to the global network. That's what the architecture looks like. It's very simple, fast, easy to administer. Let's talk about the two trends of cloud and mobility. And we're then going to wind down relatively quickly. The notion of cloud really has to do with being able to access information services from large-scale data centers. And the notion of mobility means that, look, I should be able to do my science experiments and my computation on my iPad no matter where I am in the world. I should not need to be in a specific location. So together, by having a cost-effective network which provides you access to these services and these facilities in a mobile way, can actually support the function of science and democratize science much more than it is today. And that's why these two trends are really, really important, and they're two sides, two faces of really the same coin. Let's spend a few minutes on virtualization. When people talk about virtualization, they usually think of virtual machines because they think that only computing needs to be virtualized. Well, the fact is that all infrastructure needs to be virtualized because that's the way that you get cost-effective use of the infrastructure. The real objective is to permit efficient sharing of the infrastructure without imposing too many constraints on the users. If we had enough money, we'd obviously build infrastructure for everybody. But because we don't, we have to share the infrastructure. And we want to do it in a way which is cost effective and doesn't impose constraints. The additional objective is that we want to provide independent playgrounds for experimentation. If people want to do research on networking itself, you have to be able to carve out those special virtual networks where people can play with so that it doesn't disrupt regular use of the network. We believe that there are 6 abstractions that are needed to be implemented. One is the notion of virtual data centers. Inside a virtual data center, you need virtual machines, virtual disks, virtual appliances, and virtual LANs, which are collections of VMs connected together. Of course, you need the notion of virtual private network, which actually collects together VMs inside a data center with VMs inside other data centers to the actual users that are using them together. So the notion of VPN can tie together the entire computing and communications infrastructure to the end users. And then finally, the network is the place where security policies have to be defined for the obvious reason. Now, VM and virtual disk technologies today are not at the point where I/O-intensive applications can be just implemented willy-nilly. But coming advances will get them to the point where this will happen. So what you can see with virtualization is really you should be able to have slices of the entire infrastructure separated in such a way that sets of users can interact with sets of computation devices over a virtual slice of the core without really interfering with each other. And they can really pretend that they have their own infrastructure even when they're sharing it. That's the goal. Last point is programmability. We believe that the R&E community has very specific needs to combine virtualization with the ability to do experimentation. And to do this, you need to have the right kind of programmable network elements. And there's been a very good attempt to do this, which is OpenFlow. Now, unfortunately, OpenFlow, while it has one idea right, which is this idea that networks should be programmable, the actual primitives that it provides are actually quite limiting in terms of what can be done in a scalable and cost-effective way. What we are trying to do is provide an open, programmable software ecosystem which gives you the right primitives and actually allows you to do this in a very, very cost-effective way. Obviously, we will also implement OpenFlow primitives where they are feasible, but they're not feasible at scale. So in summary, the biggest trend in the industry is this new information infrastructure, which is based on consolidation, centralization, simplification, virtualization, and programmability. And the overall architecture consists of mega data centers on the one hand, an integrated optical and packet switch supercore, a scalable rich services edge, and a very simplified access network. And I believe that this architecture is directly applicable to the R&E infrastructure. Thank you very much, and I'll take questions.
Thanks a lot for your very inspiring talk. We now have some time to take questions. Would anyone like to ask a question? Yep. Now we can see it a little bit better.
There must be at least one question.
Yeah, there is one. I have a question for you, and it relates basically to the beginning of your talk where you started to describe this basically this ecosystem with this positive feedback.
Yes.
And now the ISOC has some time ago released a set of visions for the future. And what you describe pretty much matches the first one, which is their preferred model for the future, where this positive feedback works. But they see this endangered in several ways, so that the network gets partitioned, politics have their saying, or big companies influence the way things evolve. Do you see this danger, or do do you think, well, the law of physics and the law of economics are strong enough to make the case?
So this is actually, Christoph, a very big danger. And the very big danger comes from when you have incumbent companies, they do not have any interest in changing the way things are done today. That's one danger. The second danger is that political people usually don't care about what laws of physics say. They care much more about getting reelected. And if there are particular notions that appear to be popular, that my country's infrastructure belongs to only me and I should not be sharing it with somebody else, those kinds of trends might also work counter. So I think we who understand how this kind of infrastructure can benefit humanity at large and also benefit science and education, we have to make a very strong and compelling argument. We cannot be passive about this. I think we have to be very vocal, very active, because something very large is at stake here, which is really the rate at which we innovate is at stake.
Mm-hmm. Thank you. More questions? No, wait for the microphone.
Okay, a virtualizing network device actually means that you need to give the right to control over this device to customer, not to network operator. What do you think about this, and if this happens?
So the answer to that is that you have to be, there are degrees of control that one can give to a device. So if you give full control of a network device to an end user, you risk completely destroying the network. The network may not work at all. So the way we'd like to think about it is that there are, in a networking device, is implemented in layers of application programming interfaces. The lower layers should not be made accessible except to experts, because otherwise you will not get anything to work. Our experience is that even when you have experts, making these things work is actually not so simple. On the other hand, when you can easily give access at the higher layers to end users, where they can have some control, limited control on the behavior of the network without disrupting other users. So there is a very nuanced way in which the control needs to be given, and of course it is possible. Thank you very much. Christoph, thank you.
Now we talked about the new network, and I have a small present to give to you. It's called A History of International Research Networking. So basically, it's about the old network.
Thank you very much.
You're welcome.
Okay, thank you.
Our next speaker is Professor Kees de Laat. He is chair of the System and Network Engineering Research Group at the University of Amsterdam. Now, the research in this group includes things like optical switched internet for data transport in terascale e-science applications, authorization architectures, and system security and privacy of information in distributed environments. Amongst his many other engagements, he serves in the board of directors in the Open Grid Forum and is acting co-chair of the Grid High Performance Networking Research Group. In his talk, Kees will now show the benefit of the new network, which has heard to researchers in many disciplines. Kees.
Okay. Thank you for your kind introduction. I'm going to give you a talk which I have actually given previously. I gave an inaugural speech in January, and I was specifically asked to repeat a part of that talk here. But I assure you that I changed and added a few things to go deeper than I did back then. So in the next 40-45 minutes, I want to give you a kind of overview of what research is happening within networks, what we do to support e-science. I will go along a number of applications and tell you a little bit what research we are basically doing in that. What you see here is basically, I do not do this all alone. In the last 10 years that I'm working on these topics, basically at the University of Amsterdam, since Antalya to be more exact, these people all have worked with me and done publications. Font size is proportional to the amount of publications they did in my group. So, where is it? So, Internet. Internet is going to be upon us. Internet started as a network experiment, which never ended. Words of Vint Cerf, I quote him for a few months ago. And it became a network for society. Well, this is one of the fields where, actually, if you look at the statistics, the Netherlands is one of the biggest, best penetrated internet countries in the world, which is very nice. But also, at the same time, the success has brought us before new problems. One is, of course, the exhaustion of IPv4 addresses. And note that at the June of 8, there's an IPv6 day where we will have a lot of activities going on. So I would actually challenge you all, certainly the NRENs and universities, to do something on that day to get your users more aware of that. At the same time, internet has become a billion-dollar business. If you look at the values of all the internet-related companies, you see here a number. And the one around New Year was Facebook, which was at once 50 billion worth. Is that a new bubble or not? You see, if you compare that with old economy companies, which is, for example, this Exxon is about 370 billion, you see that these are getting quite high. As a comparison, Apple is around 330 billion market value. To give you an idea what a billion basically is, this is a billion in $100 billets, so you can see how long you can burn your stove on it. At the same time, there are 3 axes in the internet, which we see happening. So internet is actually developing in 3 different directions at the same time, and needed to be supported with the same infrastructure. You see a kind of data axis where huge amounts of data are there. You see a lot of Google linked open data, societal data, and also, of course, much of the e-science data, the huge LHC data stores, but also from other sciences coming around. So these are the large flows which you can expect there, clouds. You see also an axis where it is the whole name of the game is very small messages, and huge amounts of that. You find there the Twitters, the social networks, and all these privacy intruding technologies. And you have here this way more real time. So, for example, television online or video conferencing, streaming, audio streaming, and so on. And these technologies have also a number of properties. If you look, what you need here is volume and speed. Speed is the name of the game. Here you need to be scalable, and you need to work on security. And in this axis, you need actually to be deterministic and real time. And that are very different things to solve, what you have to do there in these 3 realms. Now I want to give you a little perspective, take a step back, a little perspective what happened in the hardware and infrastructure. If I take all the computers which were on board of this Apollo rocket, when I was 10 years old going to the moon, all the computers together in the ground center, what they had in the lunar module, like the computers which they used to process the data, like this IBM 370 something, and what they used to control ground stations. This is an onboard computer with 36 kiloworth of memory, running at 200 kilohertz. Everything what they used together, everything what NASA owned together in 1969 is less than this iPhone. This iPhone runs circles around it. Only difference is you cannot go to the moon with the iPhone yet. However, there are actually projects, if you look for it, where they want to use a mobile phone as a control system for a rocket. You can find that online. There are some initiatives. And it makes sense because it has communication, it knows its position, it has a camera, so you can do star tracking, it has GPS, so it has accelerator meters and mobile phone. So it basically contains 90% of what a rocket needs to be steered. So GPU cards. This is the top 500 from supercomputing, and this is the bottom 500, so number 500 on that top list, number 500. So you see there's always, over the years, a certain distance between the performances of these computers. Also, if you look horizontally, what is top is in 7 years bottom at the list of 500s. Now we get these GPUs. If you look at the performances of these GPUs, you see that GPUs are also increasing in speed. They are expected to cross the bottom line here in 2013. One such thing costs $500. Every top 500 supercomputer costs typically 20 million and uses 20 megawatt. That seems to be a constant, more energy they don't want to put in, and this seems to be a kind of constant. Now, if you would put 10 million in GPUs and use all the 10 million to put the GPUs in somewhere, then you make a jump to this point. Of course, you will say, yeah, GPUs 10% efficient programming, okay, take a factor of 10 off, you are still here. So you see the GPUs are becoming a disruptive event if you can use them, and basically you see that already happening, and you saw, of course, earlier in the history also these kind of disruptive events. But GPUs are really a game changer. Data storage, similar thing. It's amazing that data storage over its entire history kept on this line. I mean, that's phenomenal. So the amount of storage you can now buy is really enormous. Who remembers floppies? Microsoft remembers floppies because in every taskbar of Excel it's still floppies. Optical networking. Also, multiple callers, putting up to 90 or 100 different lambdas, 50 gigahertz on one fiber, putting nowadays 100 gigabit in a 50 gigahertz spacing, gives you huge amounts of transport capacity basically in fibers. You all know that because that's what we are here for, isn't it? Wavelength selector switches, which allow now to do way more of these operations on photonics and circuits down on the fibers itself. I will talk later about this. And then the newer developments like hollow fiber, where you can at least try to do a little bit on round trip time, but there's a lot of research still to be done there, and it is complex and quite expensive. There seems to be a kind of constant, which is 2 to the power 10 to the power 17 bits meter seconds. At this moment is what technology more or less, in my feeling, allows. So either you do 10 to the 17 bit over 2 meters, or so you can calculate. It's a kind of curve. The more speed you want to put in one color, the more complicated it is to get it over a long distance. And wireless is also moving forward. Gigabit wireless experiments are already happening. But the wireless technology is also something where different creatures have to get adapted to. Not everybody will understand wireless as easy as we do. So, since I told you I gave an inaugural speech in end of January, it was partly, of course, introducing what research my group does, so I take a little bit, but you can also use it pattern, I guess, for other research groups. What we do is a number of horizontal research subjects: green IT, privacy trust, authorization policy, programmable networks, and so on. But we do it for a number of applications out of e-signs. So, for example, dike monitoring in the Netherlands, fairly important. Otherwise, at least the floors below my office would be underwater if this wouldn't work. I'm on the 3rd floor. Medical, life watch, so environmental monitoring and sensor grids. And so you see here a number of applications, also the NRAN, SurfNet, and all kind of infrastructure innovation, what we do. And our activities are basically those courses. We do not cover the entire matrix, but you see that some of our research is applicable for different applications and so on. So what I, for the rest of the talk, want to do is to point you to some of these subjects. You can, of course, also see that the three different axes I showed in the earlier on the internet developments, where you need to look at, also come back in these subjects. So you can bitmap those three axes on these horizontal subjects. So first thing, and I want to go through is a little bit quickly is the astronomy, what astronomy as an e-science community is currently doing, and you see what they probably need is a huge transport problem and optical photonic technology. So EVLBI, it has been presented before, but it is about combining the signals of different telescopes with the point that the further the telescopes are apart, the better your angular resolution is when you are looking at repetitive signals coming from space. So what you basically want, and what you do is then you do correlation between the signals you get. And from that signal, from the correlation, that's a kind of vector multiplication of the streams of data you get, you can very accurately find signals and pinpoint them. But the accuracy is actually inverse function of the baseline, the distance between the receivers. So it makes sense to use telescopes as far as possible separated on the Earth, which still can look at the same kind of heaven. It doesn't make sense, of course, to have telescopes we cannot look at the same source at the same time because the signals need to be correlated. Problem is, what you are basically measuring is noise. And you only know what the signal is if you have correlated it. You cannot compress the noise. So their transport requirements are more or less the spectrum width they look at and then the bits of accuracy they use. So in previous days, what they note that here are months. You came with a proposal, you got time allocated, you did your observations. Then you had huge tapes or disk packs where the signals were on. They were using GPU and atomic clocks to make sure that they had also the timing right, and they needed to phone everywhere that everybody was doing that at the same time, same direction. Then these things got shipped or put in a truck to Jive. Correlation happened there, and then after half a year, you had your results. Well, we looked at that process, of course, in the last 10 years, so we tried to improve and speed up the stuff, but this did not work out for the entire community. So what came up is now this whole Lambda network. Nowadays, these are 1 and 10 gigabit links, and the data is streamed over the network via Netherlight to Dwingelo, and similar things are also happening in the US. And this has made a dramatic improvement. You come up with an ID, you know these are now hours, you get it adjusted, your observation is running at the same time, the data is already going into the correlators, and you can actually look at your data just a few hours after that. What we are doing, and did in the last few years in a Science Foundation project, in the Dutch Science Foundation project, is look if you can do these calculations not in a hardware correlator, which was completely purposely built to do these end products, but if you can nowadays also take chunks of the data and distribute it over a grid or a cloud, and then process it there. The advantage is, well, more scalability. You can easier adapt your algorithms, and so on. So, but the amount of data, so the big problem here is not as much the computation, but the data is produced at many different places and you need to get it together. So it is really a data flow problem, what is happening here. The computation is nowadays with GPUs and with compute nodes is becoming less a problem. It is huge, but given that the hardware is enormously improving, that's doable. We have articles and posters about that which you can find easy. So another subject which I already warned you about that I would say something about is the dikes in the Netherlands. We have had in the last, I think it is now 12 or 15 years ago, we have had 2 dike breaches, basically, and strange, so that part of a town or city or something overflowed. And the strange thing, by the way, is that these dike breaches did not happen when it was heavily raining and the water was high, but basically when it was dry. And why is that? That is that then the dikes dry out, and the composition of the dikes, the fact that the dikes stick together, is there need to be also moisture. So it was a bit surprising when those dikes broke. We have also had near failures when there was really high water, by the way, but the dike breaches were. And you can compare that when you are walking along the beach. If you are walking along the beach, then there is a sweet spot where you can easily walk. If you go to the right, you sink away in dry sand. If you go to the other side, you sink away in the mud. So why can you walk there fairly easy in this sweet spot? And that is the van der Waals forces, which are surface forces which keep basically the sand together. And you need the dikes to have a certain moisture. So what is happening here? In the Netherlands, there is a kind of experimental dike. It's somewhere in the north of the Netherlands, near the German border, where they can experiment what makes dikes fail. So they can put here extra water, they can load the dike, they can put sensors in the dike, and they have a lot of sensors now deployed, mostly kind of sound recording. So you put kind of sound recording in those dikes. You can see they did here an experimental dike failure. You see here where those sensors are, and those sensors basically listen to what is happening in the dike. So if the dike is starting to move, then there's screeching and so on. But they have also positional and pressure and moisture detectors, but they listen to what's happening in the dike. Well, you can then learn a lot. You learn everything about sex life of the rabbits in those dikes, but you can also... another thing what they can see is if there is ebb and flood, what is it? The tide against the dike leans a little bit and then leans back. And that pattern they can also detect, and they can also infer from those patterns what the health of a dike is. So these experiments, actually the military are also very interested, because if you get long dikes with all these sensors in, they notice more than only what's happening in the dike, also overcoming planes, for example. They can very accurately track with all those microphones, with a kind of inverse phased array, track flying objects and things which make sound. But if you want to do that for all the dikes in the Netherlands, then this is an enormous amount of sensors which you need somehow to control. So what we are doing is kind of thinking about programmable networks so that networks can focus attention to where danger zones are and so on. So programmable networking and Tera thinking, what we call Tera scale flows and so on, is something we are doing in our group. So if you think about programmable networks or terabit networks, for example, what are they? So what constitutes a terabit network? Well, you can think back to teraflop computing. If you have a huge hall and you put it full with PCs, does that make it a teraflop computer? No, the only thing what makes it a teraflop computer is that you put MPI on it, for example, and that in a program you can use MPI to harvest the different multiplications of the different processors for your benefit. So it is MPI which turns this huge bunch of computers into a teraflop computer. Now think on other infrastructure. So for teraflop it is MPI, Globus and cloud nowadays. Terabytes you have DICE, MongoDB, you have different kinds of data handling, Hadoop and all these kind of things. Terapixels, Sage for example, where you can build huge walls. Sensors, there are a number of sensor grids, so for terabit we need a kind of programmable environment. So we've been working on that. We have virtualized network elements, sorry, just like in OpenFlow. But we did this about 3-4 years ago, virtualize network elements, and then make it and turn them into a kind of subroutines, and put that into an application. And we did that in Mathematica. And what we basically did is gave Mathematica a very huge data and computational problem, but gave it also these subroutines, where the subroutines of virtualized interconnect infrastructure between computational nodes could also give their topology and so on. And then you put brackets around, you say optimize and solve. And the first thing Mathematica then does is it calculates what the best topology is to solve the problem, given where the data and the computation is, and then it also solves it. So at that moment, your programmable network is becoming part of your programming model of your application. Another thing what we are doing, if the movie starts. Okay, interesting. Another thing is, why does the movie not start? Okay, here is, I think. This is interesting. Okay, what you were supposed to see, and I can show you that separately, is a touch table, which we use as a kind of user interface, where you can draw what kind of networks you want. For example, what you want to get from server to destination. And it would then be programmed into the programmable network elements, and the flows would start streaming. But in sake of time, I continue. So another field where we worked a lot with is high-end physics. And for high-end physics, you really have a transport problem. You need to get all the petabytes they produce there. You need to get them transported to the data centers where they will process that. This is a detector at CERN. Many of you probably have seen that before, but the size is always impressive. You see 2 persons. These are Dutch names, but that is equivalent for Otto Normalverbraucher or Joe Sixpack. But then it has a political dimension in Dutch, so this joke really works in Dutch. But you see the size of such a detector. For example, if you have ever been in Amsterdam, this is the palace on the dam, and the Atlas detector is really this big. I've looked at the sizes, and it is really such a wing. So these detectors are immense and produce a huge amount of data. So when they are running, they produce huge amounts of these data. This is actually one heavy ion collision in Atlas. So back in 2002, this was a slide produced by Harvey Newman, which showed how they were thinking about their data distribution. So here you see the online system that would reduce the immense data coming from the detector to a certain amount, 100 megabytes or gigabits. And then for event reconstruction, this has to be distributed to a number of tier 1s, which then would redistribute the data to tier 2s, which would do the analysis, and then tier 3. So they had a whole tiered system back then in mind, and they actually built that and used that for some time to distribute the data. Nowadays, they are taking a step back and coming up with newer requirements, which they now seem to need to use. And this is now mostly centered about glyph open lambda exchanges, where you can make connections and distribute data. So it becomes way more a kind of federated system with huge requirements, as you can see here. So multiple 100 gig transatlantic is now needed, and you need a lot of new technology to make just the data distribution of this one experiment, of this one LHC experiment happening. And there are more of these big e-science efforts going on. So what we learned by doing all kinds of experiments, big and small flows don't go well together on the same wire, as you can see depicted here. So we did a number of experiments. Nowadays, OpenFlow is the name of the game. 2-3 years ago, almost similar but less programmable was PBT, provide a backbone trunking and so on. So also kind of layer 2 forwarding scheme. And we did some experiments where we had video servers in Amsterdam. We had noise servers, so we had also a stack of machines which just would put in huge amounts of smaller flows, normal internet. And when the video server was trying to stream to Canada, the noise servers would try to kick out and compete with those few flows. And the whole point is, if you are doing all these tricks on lower layer, you expect some deterministic behavior of the flows you are doing, because that's basically what you want. You want to get rid of uncertainty on packet loss and all these kind of things. So you want to test if your bandwidth protection and your policing and shaping and everything, if that works in some way, in some expected way. So these are those results. Here you see without the bandwidth protection in that particular setup. And if we turned on the protection, then the video streams were perfectly constant and protected. So back then in that experiment it worked. So I hope that people who make the programmable OpenFlow network environment, that they also take care of bringing that determinism in. I want to say a little bit how scientific research basically goes. You go to a coffee break and then you eat the cookies, and then you use the napkin to make a plan. This is what I did with Lars Fischer about 3 Terena conferences ago, the one in Brugge. We came up with some kind of idea. Wouldn't it be nice if I could have a transmitter at the University of Amsterdam, getting that directly in photonics, letting it in Hamburg just photonically going over to your Nordinet photonic system. You couple it out in Copenhagen. You put it there into a university, and there's the other laser. So the rest is just transparent, no batteries included. We signed it both, and the experiment was then done in the subsequent year. And you see here that poster with the engineering, with the signal-noise ratio and so on, was executed by SurfNet, back then still Nortel, Nordinet, Telindus, and Sarah. Nowadays we are doing similar experiments. We showed that also at the Glyph meeting at CERN in October last year. We came up with a new concept, a kind of flight case with a number of equipment in, with such a wide area, with a long haul 40 gigabit or 100 gigabit interface. At this moment we have the 40 gigabit interface in, a number of servers. And we try to ship those to locations where it is interesting to do these kind of alien light experiments, so cross-border dark fiber alien light experiments. And what we have currently set up, and you can basically see it in the booth outside, is a setup where we have, it is remote because we couldn't get the dark fiber into this venue connected. So we have a setup at UVA, which then goes to CERN on a certain color. Here it becomes electrical, then it goes into again into an OME. And this is a long-haul laser, which basically is also used for submarine cables, can do up to 10 or 12,000 kilometers, I understood. 40 gigabit, goes through the optical system from CERN to Amsterdam, just crosses to the optical system, so it doesn't become electrical, to the one to Hamburg. Here it goes over to the Nordinet DWDM system, also just photonically, and then it ends in Copenhagen. And this span is now 2,700 kilometers, and we have that running, and outside you can see that it is transporting about 32 or so gigabit in both directions. So 65 or something in total. This is what is basically in that flight case, but you can see that later if you get. So you can find this if you go to this URL. But I can also give you a little bit of perspective of what we found when we did these initial experiments from Amsterdam to CERN in October last year. Back then it was a shorter span. It was also from our labs to CERN. And we basically got these kind of speeds. And the interesting thing is, of course, note that this was a true application, a divide and conquer computational application, what we try to do here. And these were more the iPerfs memory-to-memory combined with Divine, and we also did just around memory-to-memory experiments. So what we found is that the devil is always in the details. So if you have a PCIe card on the 8 times PCIe, then basically you are limited by the bus. The bus is 10/8, so you get 20%, 25% overhead. So basically, the raw speed you can get through the express bus is then 32 gigabit, and then there is extra overhead from IP and from the PCI Express protocol itself. So you get at 26 maximum in InfiniBand or in Ethernet, whatever you do. And what we found, and that is also and more interesting, the server architecture really also matters. We had a 48-core machine there that has an internal architecture like this. You have 4 processors where each processor has then a number of cores in it, and that total, so 12 cores, and that makes then the 48 cores. But they are on the motherboard connected in a certain bus system, and the I/O, which does the Ethernet, is then again connected to one point. So it makes a difference how close you are with the core where your protocol is running on. Is that running on this chip in a core or there? It makes a difference which core in the chip, and it makes a difference which chip. As we found out when we did the experiment. So you see here, this is just trying to do the throughput where you do an affinity. So you lock your process to one core, one specific core, and then try to get traffic in or out. And we did that for all 48 cores, and you see that there is a pattern there, and that there are certain CPUs which you should have, and others you should try to avoid, otherwise it makes 10 or 20% of the speed. So you really need to understand, if you go to these extreme experiments, what you are trying to use. This is our playfield, GLIF, Global Lambda Integrated Facility, very well known in this community, I think. So what we are doing is basically looking for the TomTom through that street plan. So how do we get for applications the routers from a certain entry to a certain exit? So we look for TomTom for complex networks. Probably very familiar here. The network description language, kind of LinkedIn for infrastructure, making all these relations and putting all the technology and so on in triplets. This is Netherlight described in RDF. So this gives us a kind of LinkedIn map and graph, including the technology and including the topology of these Lambda environments. But it is also constructed in such a way, in a web way, that every domain, every RN is responsible for its own part of that network, and you can link those files to each other. So it is a federated, distributed, multi-layer and multi-technology information system, basically, what we are trying to create here. We can handle multi-layer, so it is not just Ethernet only. I think given how often the technology changes, and given that different applications need different kind of services, you need to be able to do these kind of things multi-layer. So in TomTom terms, you should be able to jump on a bus or on a bicycle and so on. So you need and for that you have adaptation, and it's all in the model. And that allows us, for example, here to do passes over multiple layer networks where you start out electrically, you go blue, but you need to get here to a red laser, so somewhere you have to go to the electrical layer again, turn from red in blue, or blue and red, and then find your way in the photonics again till you get at the entrance. And these systems we are experimenting with can do that. But believe me, it is pathfinding is an NP complete very often and a very combinatorial problem where we are struggling with. So virtualization of infrastructure, the previous speaker also said that. We really need to master that. We need to be able to compose resources together and to describe those resources. So Federica plus Planet Lab, or let's put it that way, a kind of cloud service. It's one experiment we are working on in Novi, and the other one is Geysers, where we look at the combinations of resources. Information models take quite a leap forward here. So you see that a number of these information models are evolving and coming together, and we try to work with that in open grid forum context and together with our American friends to get those information models not only describing the networks but also what's connected to them. So the ultimate goal is that we can also describe what is connected, like for example the cloud infrastructure, or what we do within Cinegrid, the storage, the content, the transcoders, the projectors, the tile displays, the display possibilities, such that in the future these infrastructures are not used like, hey, I have this lambda, can you put something on your end and I put something on my end? No, the user wants to say, give me this very interesting movie and show it on the tile display in my living room, and please make it so. So you need a kind of information system and a reasoning system which can handle that. So the bigger goal is to make all this work top down. And at some point you can also see this as having an interface to a programmable network environment. So networks and applications are becoming aware of each other. We have done that for Cinegrid and make Cinegrid so data network aware or networks data aware, such that you can reason about these things. We run in Amsterdam a Cinegrid portal, and we are working on Cinegrid workflow planners to help the Cinegrid community with and the artist community with their workflows. So they want to learn from the e-science world how we process data in the e-science world. They want to use the same kind of methods making the new movies, because movies are more and more made digital. So they want to borrow that from us. Tonight we have actually a Cinegrid meeting where we will try to discuss future plans and so on. If you are interested to participate in that meeting, please contact Michael Krisek or Walter van Dijk or myself after this talk. So Cinegrid, it is a topology and architecture is really a huge transport and storage problem. So we are looking in that. Why do you want to do that? Why more resolution? Well, the point is, if more resolution gives apparently strong, so an increased viewing angle and so on, puts a strong emotional response into people. So the more pixels you can get and the closer you can sit to the screen, basically, the better it is. But the bandwidth you need if you are working on these kind of frames, so this is an 8K frame, are enormous. You see here 24 gigabit per second for an 8K uncompressed stream. And believe me, the movie makers want to do their workflows with uncompressed because they don't want any artifacts to come into the system before they are done with editing. But if you then want to do this stereoscopic, then you see you need already a 100 gigabit lambda. But what we think is difficult nowadays is probably just consumer electronics in a few years from now. There's now quite a lot of content produced in Cinegrid, also worldwide. If you go to cinegrid.org, there's a lot of experimental content. There's also now a huge amount of more commercial content that is really taking off. Stereoscopic takings are now done. I understood you could already see in 3D presentation here in 4K. We have seen that also in San Diego at the end of last year. And there are nowadays also movies which are basically made in computers, like Sintel is one of those of Blender, which take a huge amount. Oh, it's interesting. It's also not working. Okay. Then I have an idea where that is coming from. Okay. We try again. Yeah, okay. Having two GPUs in a laptop makes it sometimes that the computer chooses the wrong one. So these movies are completely programmed in software, completely rendered in software from Blender. And these kind of workflows, they can produce these movies in any resolution. But the rendering and making of these movies is really a huge computational task. But it is also, since it is open source, a very nice research field for us to work on. And you can download these movies, you can download the software package to calculate those movies, where all the scripts and all the workflows and everything is in. And it gives us actually basically a very nice research infrastructure. So I'm almost at the end of my talk, so I want to go through some challenges we see for us for the future. I was at the data workshop, so although here we discuss a lot about networks for the scientists, for the biology people, for the humanities people, for the astronomers, the networks are really not a problem. They don't see you anymore. Networks, for them, seems are already mostly to work. What is really the problem is the complexity and the sheer amount of data. So data archiving, publication, curation, a lot of innovation is needed there. Also, nowadays you get way more multidisciplinary e-science, so that scientists want to ask questions, system-wide questions where they need data from different disciplines, and how do you combine that data? There it gets interesting for you and us again, because that data is also typically on different places, so how do you get it together in a meaningful way? But then you get all this virtualization, so owning a computer is in a few years from now not done anymore. I mean, too much energy, why would you want that? So you want to use the cloud. But how do you then get from that a deterministic system which works for the scientific world and not just for the Twitter world, so to say? Greening the infrastructure. The DOE, Department of Energy, is now more or less becoming the Department of Less Energy. The game is how can we optimize our, and you can find that some of those initiatives in what they do nowadays. There are disruptive developments, so the fact that our hardware is enormously changing, getting solid-state disks, getting GPUs, memory doesn't cost anything anymore. So you have now network vendors who say, who are now doing this pissing game, like my switch has more memory per port than your switch, you know, they are doing that. Is that good news or not? I consider it bad news because it goes against the TCP protocols. If you put a huge amount of memory in and you never throw away packets anymore, basically your TCP protocol doesn't work anymore. You can find some URLs and some work on that. SSDs, if there are solid-state disks in your system, then the cost of reading a drop packet from the source device is not a high cost operation anymore. So you can also revisit TCP for certain file transport. You don't need to have a window because you can just as well read the packet from the source again, for example. So revisiting how the internet was built, given the current hardware, is very is something we need to do. There are also now GPU-based routers built, I understood, which can do at least 10 gigabit, We work on multi-layer glyph open exchanges, so internet exchanges of the future should also handle lower layers, and there's a lot effort going into that, with Bill Centeno also leading a task force which met at Internet 2 a few weeks back. Invariance, we need to look into invariance in light passes. Been there, done that. We have seen X25 came and went, ATM came and went, Sonnet was the big thing, came and went, Lambdas you needed to do, MPLS, and now we need to do OpenFlow. So we need to look into that. Authorization, trust, security. So if you take a step back and look at it, I tend to compare the routers with supercomputers, Ethernet switches with grid and cloud, and photonic transport with GPUs. You can get a lot out of these things, photonics and GPUs, but you really need to put an effort in to use it. But in the end, what matters is energy consumption per multiplication and per bit transport. So what we need is a TomTom kind of application, which can do also the eco route in selecting resources in our infrastructure. This is where the money comes from, at least for my group. And here you can find some interesting links. That concludes my talk. Thank you.
Thank you, Kees. We've already run out of time, so if there's one quick question, we can take it. Otherwise, I would like to thank Kees again.
Okay. Thank you.
And you also get the opportunity to look back in history and find things you did.
Okay, I hope so. Thanks a lot.
So, a couple of announcements. I would like to draw your attention to the poster exhibition, and the people behind the posters are available during the afternoon coffee break for questions, and also tomorrow. Demos, like the one just mentioned by Kees, it's one of them taking place. So during all the breaks in the Zenit and Tycho rooms, you have the opportunity to following interesting demos. And tonight there are several special events taking place, so you've got the opportunity to attend BOFs or workshops, and that's happening tonight at 6 p.m. and you will find it in the program. So that brings us to the end of this session. I hope you enjoyed it, and please provide your feedback. Your feedback is dear to us. You can do that online, and thank you for attending.